So based on characteristics of the sampling distribution of means, we know that IQ tests are normally distributed and take the shape of a normal curve. We also know that 68.26% of all random sample means in a sampling distribution will fall between one standard error and one standard error. Oh, I'm sorry, I should clarify. One standard error below the mean and one standard error above the mean. So this should be familiar, right? When we were first talking about this graph, 68%, we were describing it in the context of probability. And 68.26% of a population exists between one standard deviation below and one standard deviation above the mean. But remember, now we're talking about sample means. We're no longer talking about individual scores. And as such, we have to adjust the way that, the language that we're using in order to understand how it is that we're kind of able to even come to the conclusions that we're coming to. So the way that it works in order for you to find out the the z-scores associated with the confidence interval, I'm going to show you in just a moment. Okay. I wish this didn't come up all at once. I apologize for that. So this is part 4. Based on the information given, we can find the 68% confidence interval using the following formula. So we're going to plug in all the information. We have 68%. This is our confidence interval formula, which is the mean plus or minus the z times the standard error. So if we plug in all the information, we have 68% CI. This piece here just means that we're looking for the confidence interval at 68%. So we have our mean of 105. That was the sample mean that we calculated. Plus or minus, you have to maintain plus or minus. And the reason that you do this is because after multiplying the z and the standard error together, you're going to have to do 2 separate equations. On the one hand, you're going to have to do addition, and on the other hand, you'll have to do subtraction. So we have our formula here. So 105, remember that's our mean. We have plus or minus our z, which we determined is 1. Our z-score at 68% is 1, times the standard error, which we've calculated as 3. Okay. So in this case, we're going to take, oh, well, let me erase this so we can do 2 different. We're going to do 2 different formula. We have on this side, we're going to do 105 minus, and 1 times 3 is 3. So 105 minus 3. And then on the other side, we're going to do 105 plus 3. So 105 minus 3 is 102. 105 plus 3 is 108. So this that I've written out here, 102 and 108, that's our window. Okay, that is the window that we're working with. So therefore, the principal can conclude with 68% confidence that the mean IQ for her entire school population is 105, and that there is a 68% chance that the true population mean lies within the range of 102 to 108. As I mentioned, the idea is that we're creating this window, this confidence interval range, and we're saying we don't know where exactly the population mean is. Specifically, we don't know. But we do know that it's somewhere between 102 and 108. And so that's working with a 68% confidence. So while we are working with a 68% confidence for this particular example, as I mentioned, 95 and 99% are the more common confidence intervals that you're going to find. So confidence intervals can be constructed for any level of probability. So we did 68. We're going to talk about 95 and 99, but you could create it for 97 or 70. You can create confidence intervals for that. However, in this class, we're going to be focused largely on 95 and 99. So based on the formula, the confidence interval formula, we just need to know which z-score to use. A confidence interval of, so a 95% confidence uses a z-score of 1.96. And this can be confirmed in the unit normal table. I'll explain what that means in just a moment. 99% confidence uses a score of 2.58. Those scores will always be the case. Always, always, always. It's kind of like the unit normal table where the z-scores along the x-axis will always be that. The percentages that exist between one standard deviation below and above the mean, two standard deviations below and above the mean, so on and so forth. Those numbers are always the same. And that is the same idea that we attach to 95 and 99% confidence intervals. So whenever you're asked to work with a 95%, make sure the z-score that you're using is 1.96. Whenever you're asked to work with 99%, make sure the z-score you use is 2.58. These levels of confidence are determined by the researcher and are calculated by taking the desired confidence level, dividing by 2, and using the unit normal table to determine the associated z-score. So the way that this ultimately works is, and to be sure, I'm never going to ask you to do this, just so that you understand what's happening. If we have this normal distribution, and let's say we're trying to figure out what's happening at, remember, the window, right? The window is always relevant. So let's say we're working with two standard deviations, standard errors, really, in this case, plus, well, let's go 2.58. Oh, sorry, that should be a minus. Minus 2.58 plus 2.58. The reason that 99% confidence uses a score, a z-score of 2.58, is because 99% of the population exists between these two scores. Okay. If we were to take the 99% and divide it by 2, we would essentially be drawing a line right down the middle of this, right? And this is where the mean is at. So what that means is that if we take 99% and we divide by 2, you're going to get 40, what is it, 48.5? 48.5. So the relevance of 48.5 is that, remember that you can use the unit normal table, right? And you can find the area between the mean and a z-score, or even beyond the z-score. The area between the mean and z, which is represented by column B, for a z-score of 2.58 equals 48.5%. You are welcome to go confirm that through the unit normal table. You don't have to. Again, I'm not going to ask you to do this kind of math or mathematical thinking. I just wanted to show you this as a way of getting you to understand that these numbers are not arbitrary. I'm not just pulling 95% out of nowhere and 99% out of nowhere and just kind of presenting them to you. They relate back to this idea of probability theory. All right, so what happened to my mouse? Here we go. Okay.